In this video, we will look at other trigonometric functions. We will make use of the unit circle to find key values. Let's start with the function y equals tan x. So recall tangent is y over x. Then think about some values that are easy on the unit circle. Some easy ones that come to mind for me are when tangent is 0, which happens when y is 0, like at 0, pi, 2 pi, 3 pi, and so on. Also, going clockwise on the unit circle for negative values, y is 0 at negative pi, negative 2 pi, negative 3 pi, and so on. On top of that, we can also look at where x is 0, which means undefined since tangent is y over x. These are then where asymptotes form. So we draw dotted lines to show this. And those values where x is 0 are at places like pi over 2, 3 pi over 2, 5 pi over 2, and so on. Also, negative pi over 2, negative 3 pi over 2, and so on. This is going in the clockwise direction on the unit circle. Now let's think about another nice value for tangent. At pi over 4, tangent is 1. Similarly, clockwise at negative pi over 4, tangent is negative 1. So now we can draw the graph. It goes towards each asymptote, and the graph basically repeats. A small note, since the graph repeats, we usually look on the interval from negative pi over 2 to pi over 2. Looking at the domain, which is the x values, we can plug in anything except where the asymptotes are. The range of the graph is any value for y, and the period of the graph is pi, since the whole graph is basically between negative pi over 2 and pi over 2. The graph of cotangent is similar. Cotangent is x over y, so looking for key values, like where x is 0 and where y is 0, and where cotangent is 1 and negative 1. So x is 0 at pi over 2, 3 pi over 2, and so on. Also, negative pi over 2, negative 3 pi over 2, and so on. Where y is 0, which will make cotangent undefined, where we then have asymptotes are at 0, pi, 2 pi, negative 2 pi, and so on. And cotangent is 1 at pi over 4 and negative 1 at negative 3 pi over 4. Then the graph just repeats. The domain for cotangent function is any real number except n times pi, where n is an integer. Range is any real number. The period is pi, since the whole graph is between 0 and pi. Now that we did a couple by hand, we will do the remaining graphs on Desmos. Mainly because, like you, I rather not graph by hand. So let's look at the graph of y equals cosecant x, which is the reciprocal function of y equals sine of x. Looking at the graphs, we see that y equals cosecant x has asymptotes. And this should make sense since it is 1 over sine of x, reciprocal of sine, since sine of x is 0 at 0, pi, 2 pi, and so on. Similarly going the negative direction at negative pi, negative 2 pi, and so on. Similarly, we can look at the graph of y equals secant x, which is the reciprocal function of y equals cosine of x, meaning secant x equals 1 over cosine x. Similar to the previous example, we see that y equals secant x has asymptotes. And this makes sense since secant x is 1 over cosine x. And when cosine x is 0, makes it undefined. And those values are at pi over 2, 3 pi over 2, and so on. Similarly, for the negative directions at negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so on. Now we will look at trigonometric inverse functions. Note, the reason for inverse trigonometric functions is because many instances we want to know the angle instead of a ratio. For example, we may want to find the angle that gives the ratio of half for sine. And we state this as finding inverse sine of 1/2 gives the angle pi over 6 in this case. Let's start with y equals sine x. Because this is not a one-to-one function, it does not have an inverse function, unless we restrict the domain of sine. If we restrict the domain of y equals sine x to have x values from negative pi over 2 to pi over 2, then we actually get all the y values of the function. And now it's one-to-one, which means y equals sine x will have a corresponding inverse function when we restrict the x values to negative pi over 2 to pi over 2. To find the inverse sine function, we simply fold our original graph over the line y equals x. You may remember this in algebra when you switch the x and y's, then solve for y to get the inverse function. One other notation for inverse trigonometric functions is putting arc in front of the original function. And the domain of sine inverse is negative 1 to 1, and range is negative pi over 2 to pi over 2. This comes from switching x and y of the original sine function. We can do a similar process for finding the inverse function of cosine. First, we restrict the domain of y equals cosine x to 0 to pi in order to make it a one-to-one function. Then we flip it over the line y equals x to see what inverse cosine looks like. The domain for inverse cosine is negative 1 to 1, and range is 0 to pi. This again comes from switching x and y of the original y equals cosine x function, in turn giving us the corresponding inverse function of y equals arc cosine x. Now we look at finding the inverse tangent function. Again, we start by restricting y equals tan x domain to negative pi over 2 to pi over 2 to make it one-to-one. Then we flip it over the line y equals x to get its corresponding inverse function, known as inverse tangent, or arctan x. The domain for arctan x is from negative infinity to infinity, and the range is from negative pi over 2 to pi over 2. Now let's look at some examples using the notation. Example A reads, sine inverse of the ratio 0 gives what angle? And when sine is 0, is at the angle 0 between negative pi and 2 pi. Sine inverse of root 2 over 2 gives the angle pi over 4. in between the interval negative pi over 2 to pi over 2. Sine inverse of the ratio 1/2 gives the angle pi over 6 on the interval negative pi over 2 to pi over 2. Sine inverse of the ratio negative root 3 over 2 gives the angle negative pi over 3 on the interval negative pi over 2 to pi over 2. Next example, we look at values for inverse cosine. Cosine inverse of the ratio negative 1 gives the angle negative pi on the interval 0 to pi. Cosine inverse of the ratio negative 1/2 gives the angle 2 pi over 3 on the interval from 0 to pi. Cosine inverse of the ratio negative root 3 over 2 gives the angle 5 pi over 6 on the interval 0 to pi. And cosine inverse of the ratio root 2 over 2 gives the angle pi over 4 on the interval from 0 to pi. Next example, we want to evaluate this crazy looking expression that probably intimidates most students when they look at it. I'm here to tell you that this really just reads sine of an angle equals what? That angle is just tangent inverse of ratio 6 over 11. So let's write that like we like it and call theta tangent inverse 6 over 11, which then we can rewrite as tangent of theta equals 6 over 11. Remembering that tangent is opposite over adjacent, or y over x, we can draw a triangle with those sides labeled. Notice that all we need now is the hypotenuse for this triangle. Well, we can find that using the Pythagorean theorem. Solving, we get that the hypotenuse is square root of 157. Now we have all the important pieces of the triangle. This is because we know that sine of theta is opposite over hypotenuse. We now know sine of that inverse stuff is just opposite over hypotenuse. So 6 over square root of 157.